of gravity. I am not saying quantum theory of gravity because it is not. So, but it is quantum field theory of gravity. You can construct it. So, which means the gravitational force is transmitted via the exchange of a graviton, spin 2 field, a tensor field, right? And it does not lead us to some sensible renormalization of the theory. If we construct a quantum field theory of gravity, exactly analogous to this QED theory, then we are not able to get sensible theory. One very elementary concept I want to again emphasize, the Newton's law of gravitation and the Coulomb's law of charges. In Coulomb's law of charges, we have E1 E2 by R square gives you the force, okay, the electrostatic force between two charges. So M1 M2 are also magnetic charges, kind of magnetic charges, okay, M1 M2 by R square multiplied by the Newton's constant G. So that gives you the strength of the gravitational force. That gives you the strength of the gravitational force between two masses M1 and M2. There is a singularity. As R goes to 0, it blows up. As R goes to 0, this also blows up. The Newton's force also blows up. So, in these three theories, QED, QCD and electroweak theory, without knowing or even knowing, maybe we were not so conscious about it, but Heisenberg uncertainty principle was playing the role in this entire renormalization theory. Mr. Heisenberg might not have realized it when he wrote down his uncertainty principle almost 100 years ago now. So, but it has deep implications because the electrostatic singularity at R equal to 0 in the electrostatic force Q1 Q2 by R square is smeared out by the Heisenberg uncertainty principle. So here delta x is x cross by delta p. So when delta x goes to 0, delta p goes to infinity. When you make, I have calculated all these diagrams that I just now showed you explicitly up to the end. If you do that, then what happens in the intermediate integrals? The energies and momentas, they become very high, they can go very high, almost infinite values. As you know, so when delta x goes to 0, delta p goes to infinite, so they go to extremely high values, almost infinite values, and that causes the problem. And to resolve that, we needed the renormalization procedure to handle those infinities. That means we have to somehow modify this law for gravity theory. And except string theory, in all other theories like supergravity theory. So you consider any theory like, let me say the simplest theory, scalar field theory, or vector field theory, or spinor field theory, whichever you like. And you, first of all, you generalize it to include gravity. So put this theory in the background of gravity. So your volume element d4x goes to okay, and your we have seen this, that for including gravity theory, we have to have this G mu nu, a function of x nu, not like a Minkowski matrix tensor, which is fixed, okay, and you have flat axis. If you do that, then gravity would disappear. So if you put in gravity, and the square root of the G is the determinant of this, and so okay, you can just write in this. G is the determinant of G alpha beta, and here so you consider a field theory, you put it in the gravity background, which means you do these things, no longer flat space but a curved manifold, and as we proved last week, that curvature of manifold implies gravity, and gravity implies curvature of manifold. So curved manifolds imply gravitation, and gravitation implies curved manifolds. This we considered in details last week. So you put a theory, and here you put the L, you put minus G, and you put this, and now you supersymmetrize this theory. So that would be a supergravity theory. Okay, or you can do vice versa. You first consider a supersymmetric field theory, and then you put it in the gravity. So make the manifold curved, and change your volume element to square root of minus G times G4, and this is no longer 1, but it has some value because this is non-flat. Now it's curved. So you can either consider a field theory, put it in the gravity background, and then supersymmetrize it, or consider a supersymmetric field theory and put it in the gravity background. Okay, so that is what all those theories. There is a class of theories, you can look into that. They are called supergravity theories. Okay, but you see, in all these theories, irrespective of all our efforts, this situation remains unchanged. Okay, so all the efforts towards the construction of a quantum theory of gravity, they eventually fail because of this. This is the simplest way of putting it. Now let us see what we can do to this. So now now let me say so we modify our Heisenberg uncertainty principle. From this thing is for zero-dimensional objects, zero-dimensional particles and fields, if you like. And this is for one-dimensional objects called strings. Right? So what happens now? Delta x does not go to 0, and delta p does not go to 0. Delta x goes to some x min, which is of the order of the length of the string, which is Planckian. So Planckian length scale 10 to the power minus 33 centimeter, and delta p does not go to infinity anymore. And if you construct such a theory, then immediately you get rid of the infinities. You get a sensible quantum behavior from your theory. So what is actually happening here is that if I had this for a zero-dimensional QFT, now So, and here you see any three word lines meet at a vertex. In all the three field theories corresponding to three fundamental forces, QED theory, QCD theory, electroweak theories, all the vertices are like that, zero-dimensional vertices. But if you spread your vertex, so it's no longer a zero-dimensional vertex here, but a spreaded vertex. Vertex is spreaded in space and time. So this is for the open strings and this is for the closed strings. So everything in string theory can be described in terms of these vertices, and the origin, conceptual origin for this is what we have just now learned.